This lecture is on the motor principle, and we're going to introduce a new physicist here. His name is Michael Faraday, who's very famous in the field of electromagnetism. So Michael Faraday, he knew that Ørsted showed how a magnetic compass needle can move because of an electrical current. But his idea was that the reverse could happen. He thought that a magnet can be used to move a current carrying conductor. So he created this little experiment here where he had a piece of wire that was able to freely move around a permanent bar magnet. When he flowed electricity through that wire, the field of that wire interacted with the field of the bar magnet, and the wire started to move. That is essentially the first electric motor. So this copper wire in Faraday's motor moved because the magnetic field in the copper wire interacts with that magnetic field in the permanent bar magnet. And he determined that the magnetic field of the permanent magnet exerted a force on the current carrying conductor. So where the two interacting magnetic field lines pointed in the same way, they tend to reinforce each other, which produces a strong magnetic field. And where the two interacting field lines are pointed in opposite directions, they cancel each other out, producing a weak field. This difference in field strength results in a force to the right on the conductor. So in this case here, on the left side of this conductor, we have a strong field here, what's working together. Here we have a weak field. So because the strong field's on this side, it'll tend to push this to the right. The movement of the current carrying conductor in an external magnetic field is determined by the motor principle. And the motor principle states that a current carrying conductor that cuts across external magnetic field lines experiences a force perpendicular to both the magnetic field and the direction of the electric current. Here's another way to write that. So the magnitude of the force depends on the magnitude of the external magnetic field and the electric current, and the angle between the conductor and the magnetic field it cuts across. The direction of the force depends on the direction of both the field and the current. Copy this slide down for the motor principle. You may want to copy it down, pause before you do, because there's quite a bit to write. So the motor principle, there's a right-hand rule for the motor principle. Here they're showing it with a palm. I have a different way of doing it, so I'll show you that with your hand and using a kind of a three-dimensional XYZ relationship. Let's show you that way with each of these three different situations. The first, we have our magnetic field, of course, goes from north to south, so it would be pointed down in A. Our current would be going out of the page, so your thumb would be pointing towards you, and then your middle finger would be the where the electromotive force moves. So I'll show you this method of I'll show you how to use this right-hand rule using your fingers with each of these three examples. And in the first case, we have our our magnetic field going from north to south, so that would be pointing down. The conductor would be pointing towards you, so we'll see where the direction goes. First, let me turn the camera on and see if I can. So I have them both on the screen now at once. So here's my hand. Try to do this with your hand. So move your index finger up, your middle finger to the side, and your thumb pointing towards yourself. And this arrangement, how I have my hand, you can move your hand in a number of different ways. But if you keep your fingers sort of set like this, your thumb pointing one direction, your index finger pointing in another direction, your middle finger pointing in another direction, there's a 90-degree angle between each, 90 degrees there and there. So this is the arrangement you can use for the right-hand rule for the motor principle. Your thumb represents the direction of your conventional current flow. Your index finger represents the direction of your magnetic field. So when you're outside, an external magnetic field means your index finger points towards the south pole. Your middle finger points in the direction of the electromagnetic force. So let me reorient my hand in such a way that my electric current is going up, so I'm pointing towards myself with my thumb. I then have to turn my hand and point down for my to represent my magnetic field, and my middle finger is pointing to the right. So for A, my electromotive force will be to the right. Let's look at the second one here. For this, the only thing that's changed here is the direction of my thumb. Instead of pointing up, I'm going to point my thumb down, so you can't really see it too well. So I make my hand arrangement like this again. I point my thumb down. I point my my index finger around here. So my electromotive force is to the left. So thumb is the current going down. This is the direction of the magnetic field. Sorry, I guess I should say going in, going down, and then my finger here goes to the left. Let's do the last one here, and I can do this one by putting it up. I think, maybe over the side. So here my current is going down. My field is going this way to the left. You can't see my middle finger, but it's forced to go down. So my force would be represented by an X. So a circle with an X in it. One of the first practical uses of the motor principle was the development of meters for measuring electrical quantities. The galvanometer shown to the right is a sensitive meter for measuring current. So looking at a cross-sectional view, we see the current is directed into the page on the right side and out of the page on the left side. Using the right-hand rule for motor principle, we see that the loop is forced down on the right side and up on the left side. This causes the needle to rotate toward the right side of the scale. How would increasing the number of loops in the looped conductor of a galvanometer affect its operation? The more loops we have, the more sensitive it would be to current flow. Would the needle move in the same direction if the leads were reversed? No. So the change in current would mean there would be a change in the direction of the magnetic field and the change in the direction of the force. Another application of motor principles is for any type of electric motor. And you can probably think of a number of different things that use electric motors, from toys to vehicles, and even anything that really needs to move, like that needs an engine. So an elevator would need an electric motor. Any sort of device that is moved through electrical power would need a motor.